So now that we have defined polynomials, our next order of business is to take a look at their graphs. Now we're going to be doing a lot of graphing here. We're going to be using our graphing calculator, seeing pictures, but there's a lot of things we can say about a polynomial graph in terms of definition. And so that's what I'm going to basically do here. So you kind of, maybe it's characteristic or theory. And what I'm going to do is really rely heavily on what we know about lines and quadratics. Because if we can just remember what happens with lines and quadratics, we can get a really good feel for just about everything else. So one thing about a polynomial graph is it's what we call continuous. That's one nice feature about a polynomial graph. This has a very technical definition, a very calculus-oriented definition, but basically for our purposes right here, we can basically trace the graph without lifting our pencil or pen for all x in the domain. So that would be a layman's way of saying what continuous is. So we can basically, that's the word trace. So we can trace the graph without lifting our pencil for all x in the domain. So a lot of our piecewise functions are not polynomial graphs, right? Because we saw in the past that a piecewise function broke into pieces, and so you notice as I trace this function, I eventually have to lift up my pencil to continue the graphing. Now each piece is made up of a polynomial, but a polynomial graph is going to have no breaks basically. So there's no breaks in our graph. Okay, another graph that we've seen, right? I think this is our reciprocal function. This has a break, right? I'm tracing, I have to lift up my pencil, and I got to trace again. So 1 over x is not a polynomial. As a matter of fact, it doesn't fit the definition, right? Because we raise it to the -1 power. All right? And then even something like this, right? What's nice about this guy, right, is this is continuous, right? We've seen these before. Right? That would be another piecewise function. The good news is this is continuous, right? Because I can trace this graph. Let's assume it goes on forever. I can trace this graph without ever lifting up my pencil. But we know that there's, because of these little sharp corners from our piecewise function discussion, we know that this, right, has a different rule for this piece and this piece and that piece. So that brings us to our next definition. One thing about polynomial functions is their graphs are smooth, meaning that there are no cusps, or there's no corners, if you would. So this, even though it's continuous, this would not be a function of a polynomial graph because there's a corner and there's what we call a cusp. So we have a nice smooth transition. Looking in terms of other definitions, we've talked about absolute and local extrema, particularly local extrema. When I hit that local extrema, right, I have a nice smooth transition from there. I'm not going to have a corner, right, or some sort of cusp at that high point or low point. My curve is going to just go smoothly into that curve right there. So we have nice smooth curves, if you would. All right. Same thing if we hit a bottom point, right? We're going to slowly transition from increasing to decreasing real smoothly, as opposed to a corner or some sort of a cusp. Okay, so those are some very, very important items with regard to our polynomial functions and their behaviors. Another interesting thing is that it turns out that the number of turning points that we have, let me just go ahead and state the theory, that if I have a polynomial of degree n, then the graph will have at most n minus 1, what we call turning points. I actually like to call them concavity changes. You'll see what I mean by that as we do more stuff. Or what you guys have playfully called local extrema. Okay, so when I hit a low point or a high point, that's what we call a turning point. And the reason why we're calling it a turning point, let's just go ahead and draw a local max, right? This is a local max there. But what's happening is we're going from increasing to decreasing. Okay, and so that is what we call a turning point. So we already kind of get a feel for this polynomial because if we were talking about a line, let's say f of x equals sum mx plus b, right? This n is equal to 1 here. So how many turning points do we have in a line? Well, n minus 1 would be 1 minus 1 being 0. And of course, if we graphed a line, we can see that it has no local extreme. It has no hills or valleys. So there's no area where we can turn, right, go from increasing and decreasing. This is always on the way up. So there's that theorem. Of course, the other one we have is ax squared plus bx plus c. Here, n is equal to 2. So how many turning points do we have? Well, n minus 1 would be 2 minus 1, which is 1. And what do we know about a parabola? All parabolas either opening down or they open up. And so we can see that we have one turning point, whether it's a high point or a low point with regard to that. So with this theory, that means that if we have a cubic graph, x squared cx plus d, right, this cubic graph will have at most 2 turning points. All right, so when n is equal to 3, n minus 1 is 2. And the key word here is at most, because we do know from previous experience, if we were to graph x cubed, right, x cubed actually has no turning points. And this is what I like to use in concavity, but notice the concavity changes were kind of cupped downwards and we're cupped upwards, so there is a concavity change going on. But there's the key word about at most. Doesn't mean we have to have exactly n minus 1 turning points. At the most, I will have n minus 1 turning points. And so there's some theory at you guys there with regard to that. And then last but not least, the next thing is what we call end behavior. One very important or unfortunate thing about a polynomial is that the end behavior is unbounded. And what I mean by the end behavior, let me use a little bit of calculus here. We're talking about x going to infinity or x going to negative infinity. So what is happening here is on my grid, if I let x go on to infinity, so if I would move forever this way, or if I let x go to negative infinity, I move forever that way, a polynomial graph is going to be unbounded, meaning that it's going to go up forever or down forever, or it's going to go up forever or down forever. So it's going to either approach infinity or negative infinity, depending on some other conditions of our functions. Okay, and that's what I mean by unbounded. So it's never going to taper towards some, what we'll call horizontal asymptote later on in our class. It'll always, at some point, as we let x get bigger and bigger and bigger in either direction, the function's just going to explode on us, if you would. It's going to approach positive infinity or negative infinity. And it turns out that everything comes down to lines. All right, so if we think in terms of an odd n, all right, our classic case is to think of a line. So we know for a line, if mx plus b, if our m is greater than 0, then our line's going to be increasing. It's going to basically be going up forever and ever and ever. So in terms of the unbounded behavior, right, it's going to infinity in this direction, but negative infinity in that direction. Of course, if m is less than 0, that means my function is on its way down, which means the function is going to unbounded to positive infinity in that direction, but negative infinity in that. And it turns out that if you can just remember what a line does in terms of the lead coefficient being positive or negative, you know what x cubed is going to do, x to the 5th is going to do, x to the 7th. Because there's more powers, we're going to have a little bit more curvature, if you would. And you can see it actually here in the x cubed, right? The number out in front of it, it's 1, so it's positive. And so what's the function basically do? It's on the way up. It's unbounded to infinity in this direction and negative infinity in that direction. And we know that if I was to multiply by a -1, what's going to happen to that graph? Well, it's going to basically flip through the x-axis. And so now it's going to positive infinity here and negative infinity there, and it's essentially on its way down. So let me go ahead and start to summarize this idea kind of in a table about our end behavior. So basically, our end behavior, right, if our degree is odd and our lead coefficient is negative, or our lead coefficient is positive, here's basically what's going to happen. The graph is generally decreasing in this case, right? So it goes to infinity on this side, right, when x is going to negative infinity. Let me put in an axis there, right? Or when x goes to positive infinity, then the outputs go to negative infinity, right? And I guess that's f of x. So f of x is going to infinity, f of x is going to negative infinity. Okay, so are the outputs. And then if the lead coefficient is positive, that means that my graph is generally on the way up. So as x goes to infinity, f of x also goes to infinity. As x goes to negative infinity, f of x also goes to negative infinity. So it's generally on the way up. It's increasing. Okay? And then with regard to an even degree, all you have to do is think about what we've learned about x squared. So let me come back to here. What do we know about x squared? Well, if we talk about 1x squared, then the end behavior, right, it's going to infinity in both directions. But if we considered negative x squared, then we know that that's a parabola opening down, and it's actually going to negative infinity in both directions. And it turns out that x to the 4th, x to the 6th, x to the 8th, x to the 10th, I don't care what you do, but an even degree will have the same action as your x squared function. So that's kind of a cool thing to know. So this means then if our leading coefficient is negative, then our function, right, so here's our x and our y, it might have all these waves and stuff, but eventually as x goes to negative infinity or as x goes to positive infinity, f of x goes to negative infinity in both directions, right? So negative infinity and negative infinity. If our leading coefficient is positive, then here's my x and my y. The function can do all this crazy stuff, but eventually it's going to positive infinity in both directions. And so as x goes to negative infinity, my function goes to positive infinity. As x goes to positive infinity, my function values go to positive infinity as well. So there's some theory. Why don't we go take a look at some graphs and try to decide which polynomials fit certain types of graphs, and we'll continue to work on this end behavior. I think it just takes some practice, but if you just think in terms of lines and you think in terms of parabolas, you can't lose. We already know what lines do with negative coefficients and positive, decreasing and increasing, and we know what parabolas do with negative, we're pointed downwards, and with positive, we're pointing upwards. Everything else basically follows suit with these particular type of degrees in polynomials. All right, so enough theory. Let's go look at some graphs.